Well, I have a little less than an hour and a half available right now, so this will be another one of those cases where the unit is split into two recordings, I think. Section 13 kind of continues what I started last week, and actually to some extent even into the week before. The branch of physics that looks at heat and temperature and things related to that, thermodynamics. The study of thermodynamics, as far as the history of it, if you go back into the late 1700s, steam engines were getting to be a really big thing, okay? There were a lot of money, or there were a lot of people making a lot of money off of factories and mines and things like that that used steam engines for various purposes. And if you had a factory that was powered by a steam engine, you bought a lot of coal every year. And if somebody could figure out how to make a more efficient steam engine so that you didn't have to buy as much coal, they could probably sell a lot of those more efficient steam engines and make a lot of money themselves. And so there was a good deal of motivation to better understand the principles involved in some sort of a system that has heat flowing through it. The original example being a steam engine, but of course there's a number of such devices today. There's several different types of engines, and also a heat pump like an air conditioner or a refrigerator is governed by the laws of thermodynamics also. Altogether, actually, there are 4 laws of thermodynamics, which rather oddly are numbered 0 through 3 rather than 1 through 4. But the most significant are the first and the second law, and those are the only ones I'm going to bother covering in this course. So the first law, the first part of section 13 is about the first law, and the second part is about the second law, and I wouldn't be surprised if that's where I ended up making the break between the two recordings. But the first law is just a restated version of our old friend conservation of energy that I've been talking about for quite a while now. You have this basic general universal principle, conservation of energy. If you phrase it in a certain way that makes it a useful problem-solving tool in mechanics, we call that the work energy theorem. If you take conservation of energy and phrase it in a different way that makes it useful for thinking about thermodynamics, then we call it the first law of thermodynamics, and it looks like this. And underneath it here, it says what the 3 things in it stand for. E-int stands for internal energy, okay? Internal energy, like it explains down here, means the total energy of a system's molecules. The simplest system you could be talking about would be a container filled with some sort of a gas like helium or argon, where there's only 1 atom per molecule, okay? If, you're probably tired of looking at that. Probably tired of looking at me too, but at least it's variety. If you have just a single atom in each molecule, like you do with helium, then the only kind of energy that those molecules can possess is translational kinetic energy. If you've got a party balloon full of helium, each helium atom in there is just shooting around, goes across, bounces off the inside of the balloon, goes over here, bounces off the inside of the balloon again, comes down here, bounces off another helium atom. And as they zip around like that, they've got, each atom has some kinetic energy, 1/2 mv squared. If you add up the kinetic energy of all those molecules, then That's the internal energy of the gas. If you have, well, even air, okay, oxygen and nitrogen both have 2 atoms per molecule. And even with that, things get more complicated. If this is an oxygen atom and this is another oxygen atom, so the 2 of them together are an oxygen molecule, in addition to moving, blown the balloon full of air, in addition to moving across the balloon, like I was just talking about with the helium, the 2 atoms will vibrate within the molecule. So you've got some energy involved in that. And at the same time it's doing that, the molecule can also rotate. So actually, if I try and do everything at once, I'm probably not this coordinated, but if they're vibrating and they're rotating and they're moving across the balloon, so you add up that rotational energy and that translational energy and that vibrational energy, and the total of all of that would be the internal energy of the gas inside that balloon. And that's just a gas with 2 atoms per molecule. You get involved with liquids or solids and things start getting complicated because, you've got energy, you've got the latent heat, like I talked about in section 13, or this is 13, that was section 12, where, the heat, the energy that's stored in the bonds in a liquid or a solid, the whole thing about why it's worse to get burned by steam than it is by water and all of that kind of thing. Anyhow, you add up all those various internal forms of energy, and that is the internal energy of the system you're talking about. It does not include any external form of energy. For example, if you have your party balloon full of helium and you give it a ride in an elevator, so that now when you get off the elevator on the 3rd floor, it's got more potential energy than it had down on the 1st floor, you don't count things like that. It's what's going on within the balloon that goes into or whatever you're talking about. What's actually a little more common to be talking about than a balloon is, I think I waved this around last week also, if you've got a piston in a cylinder, so you can adjust the volume by moving the piston. Because many of the applications involve engines, and because the most common type of engine is a piston engine, that the gas inside of a cylinder like that one is quite often the system that you're talking about here. But anyhow, that's what internal energy is. Q is the amount of heat added. I talked about heat quite a bit last week. W for work. So I guess I need to raise that up a little so you can see the picture. So there's usually a little more to an engine than just this, but a very simple engine might, well, this is not actually too terribly different than the way an old style steam locomotive is built. There's no transmission or anything involved on one of those. You've got actually a steam engine is a really good example to be keeping in mind through this stuff. When you're first learning about how things work, it's not a bad idea to start with the obsolete technology, because a lot of the same principles are still used, but the stuff from the 19th century is simpler. It's easier to understand. And once you see what's going on with that, you can then kind of build on it. If this is steam in here, you've got a nice uniform temperature and pressure, whereas if it's a gasoline engine, the spark plug fires and you've got a flame front advancing through the cylinder, and you've got a temperature gradient and a pressure gradient, and so the simplest example would be some Civil War era steam locomotive. Or actually, you don't have to go that far back. They were still building them in this country into the 1940s. Anyhow, whatever kind of gas it is, steam or the gases in a gasoline engine, it's under pressure. And the pressure pushes the piston outward. Let's consider just a small amount of movement of the piston, because if it doesn't move much, then the pressure doesn't change much, and that makes things simpler to talk about. You don't have to bring any calculus into the discussion. So originally the piston went from this dotted line to that dotted line, and a very short amount of time later, then the piston goes from the solid line to the solid line, being pushed along by this force, which comes from the gas pressure. As the piston moves, it pushes this connecting rod, which makes the wheel turn and does some sort of useful work. Work is equal to force times distance. The cosine factor is equal to 1. If you remember from, what was it, section 6 maybe? It was force times distance times the cosine of the angle. But there's only one direction the piston can go. It has to go right straight down the cylinder. It can't go off at some angle to the side. So it's just the cosine of 0 degrees, which is 1. And the work is just the force times the distance. I introduced a factor of A over A. That's just like multiplying by 1. So that's mathematically allowable. A is the area. To be a little more specific, it's the area of the end of the piston, okay? The area which is in contact with the steam here. The area over which this force is distributed, to say it another way. And I slide the one A underneath the F, and I stick the other A next to the D. Force per unit area is pressure. That's how much pressure this gas is under. A times D, that would be the volume, this little pancake shaped volume between my fingers there. A very, very short cylindrical volume. The volume of a disc or a cylinder is its cross-sectional area times its length. Well, the cross-sectional area is A, and the length of that small region is D. And so A times D is the volume of this little bit from the solid line to the dotted line, which is the change in volume of the gas. The gas used to go from there to there, and then in the end it goes from there to there instead. The change in its volume would be the volume from there to there, which is A times D. So the moral of the story is that the work done by the expanding gas is the pressure times the change in the gas's volume. So that's equivalent to the original definition I gave for work several weeks ago, force times distance. But when you're dealing with a gas, quite often it's more convenient to talk about things like pressure and volume instead. Let me raise that up a little more. People are talking about thermodynamics. Quite often it's useful to, it's always useful to draw pictures of things. How do you draw a picture of the changing state of a gas? With a graph. And the usual graph that they find useful is pressure on the vertical axis, volume on the horizontal axis. So as the gas in this cylinder, this steam or whatever it is, increases in volume this little bit, okay? The original volume of the steam was that much. The final volume is this much. Delta V is the difference, final minus initial volume. That much of a change in volume right there. And the pressure in the gas, well, on the pressure axis, that would be this much pressure. The work is P times delta V. Notice that P times delta V is the area underneath. See, this is the original state of the gas, and this is the final state of the gas on this graph. And the in-between states that it goes through as the piston is moving would be along this line here. And notice that P times delta V is the area underneath that line. You've got a rectangular area here, and the area of a rectangle is its length times its width. In the more general case, where you let the piston move more than a minuscule amount, because as the piston goes down the cylinder, the pressure is going to drop as the gas expands. And so you'd have a graph that looks something like this. Well, it's a little more complicated to explain in this case, but it's still true that the work done equals the area under the graph, just like it was equal to the area under this graph right here, P times delta V. So we're not really going to get involved in how you find the area underneath a curve like that. I've got some examples rigged up where the graph is just line segments, so you can get the area without having to know anything about integral calculus. But the area under the graph is the work done. So time for me to raise that up some more. And what's on the rest of the page is a couple of examples for you to practice on. I should put that about there. If you need a hint for number one, if you don't, stop me now and go ahead and do it. But if you need a hint for number one, this is a question about the first law, right up at the top of the page there, the first law. You're given some numbers, you have to stick it in the first law. I didn't write the answer under it because if I did, it would kind of give the whole thing away, and I wanted to make you think about it. And assuming you have thought about it now, we're supposed to pause it. Didn't you pause it? But if you got 350 joules, you are correct. If you got 50 joules, you are wrong. Physics can be so judgmental sometimes. It says, without getting into the equation, I mean, it's always a good idea to keep in mind what the equation means, what's going on behind all those symbols. And as far as just conceptually, think of it this way. You've got, it says 200 joules is added in the form of heat. Okay, so remember, heat means energy that flows due to a temperature difference. So you've got maybe a cylinder like this one. It's got some air in it. The air inside the cylinder is the thing the question is about. What if I took this and I threw it in a big pot of boiling water? Some heat would flow through the walls of the cylinder from the hot surroundings to the cooler air inside. Okay, that's what heat flow means. And so 200 joules is added that way. The question also says that 150 joules of work is done by pushing the piston inward. Now, When the piston goes outward, remember the picture I had on in the note packet there? When the piston goes outward, that's what pushes on the wheel and makes it turn and makes the car go down the road or whatever sort of work is being done here, okay? If you, I should close the valves. If you push the piston inward, compressing the gas, that does work on the gas, okay? If the piston is going outward, you see where the energy comes from, that's delivered to that wheel and becomes useful work. Where that energy came from is it started out being the energy of the molecules moving around in the gas, the internal energy. Well, if you think of one, or maybe I should just draw a larger version of this. There's the walls of the cylinder, and there's the piston, and along comes a molecule, one of many. It comes along, and it's just going along, minding its own business through empty space. Well, not quite empty space, but all of a sudden there's this piston in the way, and it bounces off. Think of it like an auto accident, okay? If you're going down the thruway at 70 miles an hour, and you come up behind somebody that's going 60 miles an hour, and you're fooling around with your phone like you're not supposed to, and you drive right in the back of them, well, I mean, that's not good. You're going to have to pay for some mangled up taillights and things like that. But you don't receive nearly as much of a jolt as if you get a head-on collision. If you're going 70 and somebody's coming 60 the other way, you know, everybody's dead. You get a much greater jolt when things are going in opposite directions than when you catch up to it from behind. And so if this if the piston is moving outward and this molecule comes along and bounces off of it, the tendency anyhow is for the molecule to be going slower. It helps push the thing along, and it receives a little bit of a jolt, which slows it down. And, you know, it helps push the thing out. Energy, internal energy is lost. Work is done by the gas when the thing expands. On the other hand, if you're pushing the thing in against the resistance that you encounter from these things bouncing off, then you are adding to the internal energy. These molecules will get a big jolt that tends to speed them up. If the thing is headed toward it when it bounces off of it, it's going to come off of the piston going faster than when it approached. So compressing the gas does work on the gas, adding to its internal energy. When the gas expands, pushing the piston outward, the gas does work, pushes the car down the road or whatever, and internal energy is lost. So that's kind of the story behind it in words. "200 joules was added in the form of heat flow. Another 150 joules was added as you did work on the gas, compressing it. Altogether, 350 joules added to the internal energy." That's the idea in words. But as far as how the numbers fit into the formula, well, let's see. The way it's written there, different books put things different ways. basically, I don't know if I had ever said this, the idea behind the first law is kind of what I was talking about last week when I was talking about cutting the end off of something with a hacksaw and then burning yourself. Basically there are two ways to add to the internal energy of a gas. The internal energy of a gas is proportional to its temperature. With liquids and solids, it gets more complicated because of the energy stored in the bonds between molecules. But for an ideal gas, if you double the internal energy, you double the absolute temperature, okay? Triple the internal energy, triple the temperature. So the internal energy, the way you perceive it is as the temperature of the gas. Well, I shouldn't say that. A large amount of gas at a low temperature could have more internal energy than a little bit of gas at a high temperature. But for a given amount of gas, okay, if we're going to say I am talking about 1 mole of gas, then the internal energy would correspond to the temperature. This is saying that there's 2 ways of changing the temperature, two ways of changing the internal energy. You can add heat to it, okay? Or you can do work on it. Cutting the end off a rod with a saw, you're doing work against friction. That makes it get hot. Or you can cut the end off the rod with an acetylene torch. You're putting the rod in contact with a thing at a high temperature. That makes it get hot. So you can add to the internal energy either by heat flow or by work. That's what's going on here. Well, to stick the numbers in, which you've probably been waiting for me to do about 10 minutes at this point. The internal energy, the question asks about, the amount of heat added is 200 joules. Plus and minus signs are tricky here. Increase in internal energy. It's actually decreasing, this would be negative. Heat added, if heat is actually flowing out, this would be negative. The work done by the gas, if work is in fact done on the gas, this would be negative. So 200 joules of heat minus the amount of work done by the gas is negative 150 joules because work is in fact done on it. Minus cancels minus, and you get 350 joules. Second question, based on this idea that the work done in a process is equal to the area under the curve. And in a realistic situation, the curve would curve. And well, this is the reason that people who want to become professional engineers have to take calculus, or at least in theory, that's why they have to do it. But for a non-calculus course like this one, we're going to look at a graph which is a little bit less realistic, but at a lower mathematical level. It's just a horizontal line and then a vertical line and then another horizontal line. So this is the original state of the gas. This is the final state of the gas. And as the gas is changed from the one state to the other, how much work does it do? Pause it here, figure it out. If you need a hint, you can sort of visualize a rectangle underneath that part of it and another rectangle underneath that part of it, and calculate the area of each rectangle and add them together, and this should be the answer you get. And if you see me write it out and talk about it as I'm going through it. Here it is. The work done in a thermodynamic process is equal to the area under the curve on a PV graph. So the graph amounts to two rectangles standing next to each other. You know, it started here and it went along to there, and then it went up like that, and then it went over, and this is the final state of the gas here. And there really isn't a little gap in between, but I kind of wanted to make it look more like two rectangles. The height of this one, 3 times 10 to the 5th, because vertically is the pressure axis on that graph, and that's measured in pascals. The other one is 2 times 10 to the 5th for its height. On the graph there, the right-hand side of this is at 0.095, and on the horizontal axis, the left-hand side is at 0.070. So that means that from here to here is 0.025. Similarly, from there to there is actually, you know what? I'm going to kind of make a mess out of your notes. That was not quite the way to. Final minus initial. Better to do it like that. Delta V is negative because the volume is decreasing. Same thing here. The volume is decreasing. Delta V is negative. Where I got that from is 0.05 minus 0.07. One side of it is at 0.05 on the horizontal axis, and the other side of it is at 0.07. So length times width of this one length is P, width is delta V. Work equals P delta V equals the area under the graph. Fill in the numbers. And you go through the math. That first term is -6,000, and the second term is -5,000, and the grand total and I went pretty low on the blackboard there, but that's it. The work is negative because, well, same thing as in number one. Work is being done on the gas. By compressing it, you are adding to its internal energy. As the molecules collide with the moving piston, they do it in such a way that it makes them speed up. Maybe a car crash was not the best possible analogy because cars crumple up a lot. That would be a rather inelastic collision, whereas a molecule doesn't crumple up when it runs into something. That's going to be a perfectly elastic collision, which would be a little more like balls colliding on a pool table than cars colliding. Probably shouldn't use that example again. That might not have been the clearest way to look at it. Anyhow, it's time to turn the page. And at the top of the next page, it talks some more about heat. Now, heat was something that I spent a significant amount of time talking about in section 12, Q equals MC delta T and that kind of thing. When you're talking about a gas, section 12, I pretty much, for the most part, stuck with liquids and solids. Quite often when you're talking about a gas, it is more convenient to do the specific heat on a per mole basis rather than per unit mass. Okay, instead of per kilogram or per gram, the behavior of a gas really depends on how many particles it consists of. So per mole is really quite often a more enlightening way to look at things. So if you're going to describe how much gas you've got with moles instead of grams, then instead of MC delta T, the amount of heat added to it would be N times C times delta T, where N is the number, N is the same N that you've got in PV equals nRT. Okay, it's the number of moles of gas that you've got. And when it's a molar specific heat, the notation that's sometimes used is to use a capital C, whereas it was a lowercase c for the, you know, the per unit mass kind of specific heat that we had last week. Well, you know, when I'm just writing on the blackboard, a little c and a big C can look a lot alike, but that's the notation when you're being careful about such things anyhow. So either calories per mole per degree or joules per mole per degree, depending on your favorite energy unit. And that's what we'll measure this in, whereas last week this would have been grams or kilograms here instead. Now, it gets more complicated. When it was a liquid or a solid, the specific heat was just the specific heat. And it didn't really matter if you were maintaining a constant pressure or if you were keeping a constant volume, because liquids and solids aren't really compressible. If you kept a constant pressure on something, it also was keeping a constant volume. The two are pretty much the same thing with liquids and solids. Gases, no. Keeping a constant volume and keeping a constant pressure are two rather different things, as I'll explain in a moment. The specific heat of a gas varies depending on what the gas is doing as you add the heat. For reasons that I'll explain in a matter of seconds here, if you keep a constant volume, it takes less heat to run it up by a degree than it does if you keep a constant pressure. So CV is the molar specific heat at a constant volume. CP is the molar specific heat at a constant pressure. And you could imagine other types of processes which would each have their own specific heat, but these are the two that come up really often, and so that you see them in the textbooks a lot. Why the difference? Well, I've got my visual aid here. If I want to add some heat to this at a constant volume, what I would do is squirt a little bit of super glue in there so that the piston can't move. And then I would throw it into a big kettle of boiling water, and heat would flow in through the walls of the thing there, and the temperature would go up as a result. If I wanted to add the heat at a constant pressure, on the other hand, no super glue, rather, let me find something to use for a weight. The physics lab, it's full of weights. So what I would do is I would full of weights, but there's a question of getting it to the proper height. Somewhere around there. Put a certain amount of weight on top of the thing, the piston. Now, what's going to happen is the reason this keeps a constant pressure is because this is 500 kilograms. It weighs 4.9 newtons, okay? So, and the piston weighs a little bit, but not very much. So basically, I've got 4.9 newtons bearing down on that piston, and that piston has a certain amount of area, and the pressure is that force divided by that area. That's the definition of pressure, P equals F over A. So if I maintain a constant amount of force on the thing, and I drop this into my kettle full of boiling water, what's going to happen is as the temperature goes up, where's my piece of chalk? There it is. Maintaining a constant pressure means that at a higher temperature, you're going to have a higher volume. One side of the equation gets bigger, the other side of the equation has to get bigger in order for them to still be equal to each other. You raise the temperature, the air expands. As the air expands, it will lift the weight. Lifting the weight means you're doing work, okay? So, to the first law. Still on the board over here. In the constant volume case, no work is done because the piston doesn't move, okay? Work is P times delta V. Delta V is 0 if the piston has been super glued in place. Or you don't need a formula. Just think how far is your car going to go down the road if your engine is seized? If the piston doesn't move, no work is done, which means all of the heat goes into raising the temperature. Internal energy is proportional to the absolute temperature. In the constant pressure case, the gas expands, so some work is done. That means if you add some heat, some of the energy goes into doing the work, and only some of it goes into being internal energy. So constant volume, all the heat goes into raising the temperature. Constant pressure, only some of the heat goes into raising the temperature. Therefore, you need more heat to get it up a degree, and that's going to be a larger specific heat. That's the reason why there's a difference between CP and CV. And what just took me about 5 minutes to say is written here in 2 lines, because when I can sit there and think about it for a while, I'm more concise with what I'm saying, I guess. It's like that old thing about how I didn't have time to write you a short letter, so I had to write you a long one. Will you focus? Okay. Probably you're not surprised to hear that on, which page is it? Page 6 of your formula sheet. There it is, page 6. Last week we used the expansion coefficients and we used those specific heats. Well, next table down below those. CP, CV for various gases. So you will need to refer to that to answer question number 3. And here's where you pause it and do a little figuring. And here's where you unpause it and I explain it, because if you could do all this stuff without me ever having to explain anything, there really wouldn't be any point in you taking the course, would there? In both part A and B, the question asks for Q. How much heat is needed? In part A, it's a constant volume process, so you would use the constant volume specific heat, NCV times delta T. It says there are 2 moles of helium. N is the number of moles. You go into that table that I was waving around and look up CV for helium, and it says 12.5. Maybe I should write out the units on all this once. This was in moles. The unit here is joules per, it's not a very good J, that's slightly better. Joules per mole per Kelvin, so moles cancels moles like that. And the question says you're going to raise the temperature by 100 degrees. This is the part that probably caught you if you couldn't get it to work. Delta T is 100 kelvins. Kelvins cancels kelvins, and the heat, the energy will come out in joules. And you're sitting there going, aren't you supposed to add 273? individual temperatures differ by 273 degrees on those two scales. Temperature changes are the same. If it's delta T, Celsius and Kelvin are interchangeable. This 100-degree increase, maybe it's from the freezing point to the boiling point, okay? Maybe you've got a container full of helium, maybe you pulled it out of some ice water and you threw it in some boiling water. If you want to measure that on the Celsius scale, it went from 0 degrees originally to 100 degrees in the end. If you do it on the Kelvin scale, it started out at 273 and it ended up at 373. It's a change of 100 degrees on either scale. So that times that times that. 2,500 joules. Part B. At a constant pressure, this time you would use, from the other column, the constant pressure specific heat, CP. And is still equal to 2. And 20.8 is CV or CP. Temperature change of 100 degrees once again. So if you let the gas expand as you're adding the heat, it takes over 4,000 joules to get you up by that 100 degrees, rather than the 2,500 joules that it takes if you don't let it expand. Well, now it says thermodynamic processes. It's vocabulary time. Everybody's favorite. You're going to learn a couple of new words. I think I want that just slightly higher, actually. And if I put this under there, probably, and it's too high. No, that's just right, actually. Well, there's lots of ways that the state of a gas might be changed, but 3 ways that come up often enough to be given names are an isobaric process, an isothermal process, and an adiabatic process. As far as what goes on inside of a practical engine, an isobaric process is not particularly realistic, but it's a nice thing to talk about in introductory courses because it's the mathematics is simple, okay? An isobaric process is one where you maintain a constant pressure. So that would be the thing like I was talking about before, where you keep a fixed amount of weight sitting on top of the piston and let the gas expand or contract however much it needs to while maintaining that constant pressure. So for example, here we see the volume going up at a constant pressure. What's probably going on here is it's being heated up, okay? As the temperature gets higher and higher, the molecules move around faster and faster, which means they hit things harder and harder. And if you're going to keep the pressure the same, you've got to get those molecules further apart from each other so that there are fewer collisions per unit area. Fewer collisions per unit area, but more force from each collision. Keep a constant pressure that way. So the gas will expand as you heat it up at a constant pressure. But as far as what the PV graph looks like, it's just a horizontal line, which makes it really easy to find the area under it, like the example we've already done. Isothermal means constant temperature. Here, PV equals nRT once again. Oh, I guess I've got it written out over here. I don't have to write it on the blackboard. In general, PV is equal to nRT. Well, we're assuming that it's a constant temperature because that's what the word isothermal means. So if T is a constant and N is a constant, which just means the cylinder doesn't leak, and R is a universal constant, that could only change in some science fiction story. If everything to the right of the equals never changes, the gas law reduces down to a special case called Boyle's law. You don't need to know the name, but PV is a constant. Or equivalently, if you divide both sides by V, P equals a constant divided by V, like I wrote over here. Well, this is basically in some intermediate algebra course, maybe you were introduced to the function y equals 1 over x. It's a rectangular hyperbola. It's got an asymptote against the vertical axis and another asymptote against the horizontal axis. And here we're just calling it P and V instead of y and x, but it's the same function. The constant is some other number probably instead of 1, and that only makes a very minor amount of difference. It's the same behavior. So you've got something that, as you head toward infinity this way, gets closer and closer to the horizontal axis without ever reaching it. And as you head up toward infinity vertically, it kind of leans toward the vertical axis without ever getting it. And that's the graph you would have if the state of a gas was being changed isothermally. The way you would do that would be to make the change extremely slowly and in contact with some sort of a reservoir. They call it a heat sink, something that you can draw heat out of or put heat into without really changing its temperature. If you had a little cylinder that was only this big, a swimming pool full of water would make a really good heat sink. You've got, 10 or 15,000 gallons of water there. And if you dump a few hundred joules of heat into all that water or draw a few hundred joules out of it, it's not going to change temperature by any meaningful amount. So what you would want to do, well, first of all, instead of being made out of glass, you'd want a cylinder that's made out of metal because metal is a much better conductor of heat. And you put it in the swimming pool and then you compress the gas really slowly, much slower than what I'm doing here. As soon as you compress the gas just a little bit, the temperature goes up just a little bit. And that makes heat flow through the walls of the cylinder into the surrounding swimming pool. So before the temperature can rise any meaningful amount, some heat escapes into the surroundings, and that's how you would do an isothermal process. An adiabatic process. Come on. Oh, I'm just going to turn the thing around again in a moment anyhow. I'll just read it off to you. An adiabatic process is one where there is no heat flow. Q equals 0 instead of delta T, or for that matter, delta E equaling 0. Students, I have found, like to get isothermal and adiabatic confused with each other. They are actually more like opposites than the same thing. This student kind of looks at it and goes, no heat flows, so the temperature wouldn't change, right? But you're forgetting the temperature can change because of the work done. Okay, I said that to get an isothermal process, you want to move the piston extremely slowly while it's in contact with a heat sink. To to get an adiabatic process, instead of the heat sink, you want to wrap this thing with about 3 feet of fiberglass insulation. And then after you've done that, you want to compress, if compressing it's what you're going to do, you want to compress it as quickly as you can, because that fast does not give the heat any time to flow. And what little heat could flow in that very short amount of time, well, you've got the 3 feet of insulation to get in the way. So no heat flows. That's what adiabatic means. Well, as you go shoving that piston in, it does work on the gas. It adds to the internal energy. In the isothermal case, as quickly as you add to the internal energy with heat, I'm sorry, as quickly as you add to the internal energy by doing work, the energy leaves again in the form of heat. Okay, back to this thing over here again. Isothermal, you add to the, well, maybe look at it here. Heat adds to the internal energy. Why do I keep wanting to say it backwards? Isothermal work keeps wanting to add to the internal energy at the same time that heat flow removes internal energy, and therefore there is no change in the internal energy. Temperature stays constant. So this cancels that. In the adiabatic case, you do not allow any heat to flow. So you're adding to the internal energy without any compensating heat flow. The internal energy goes up and the gas gets hot. Whereas in the isothermal case, it keeps a constant temperature. So because the gas gets hot when you compress it adiabatically, oh, there we go, the graph is going to be steeper. For the isothermal case, the equation of this graph was Boyle's law, PV equals a constant. The higher temperature, you know, if you started at the same state, and well, I drew arrows going the other way, but if you're compressing it, if you started at the same state, compressing it adiabatically will run it up to a higher pressure, the higher pressure being due to the higher temperature. Okay, here you keep a constant temperature. Here it gets hot. At the higher temperature, you'll have a higher pressure. And so this graph is steeper than the one here. And what makes it steeper is that V is raised to some sort of an exponent rather than being to the first power like it is for the isothermal case. That exponent turns out to be, see, this is one of the differences between this course and Physics 131, Physics 132 actually, is I make the class sit there for 10 minutes and watch me derive this. And you're sitting there going, boy, I'm glad I didn't take that class. And for you guys, I'm just asking you to trust me or ask somebody who took the other course. But it turns out that that exponent is the ratio of the specific heats that I was talking about at the top of the page, CP divided by CV. Exactly what that ratio is depends on what kind of gas you're talking about. Remember this table here where you looked up CP and CV? There's a third column. Gamma, the Greek letter gamma, is the ratio of the other two numbers. This divided by that. In the case of helium, it comes out 1.67. For diatomic gases like nitrogen or oxygen, it's around 1.4. You get more complicated gases like methane, and it's down around 1.3. So you have to look that up for the particular kind of gas you're dealing with. And I'm going to do an example, and then I think on the next page, if I remember right, there's an example for you to do, and that'll probably get me through just about the amount of time I've got left, and that'll be the perfect place to leave off because then we'll be between topics. So probably about another 20 minutes or so. Well, longer for you because working on these sample problems takes you some time when I just kind of skip over that. But anyhow, I'm going to run through this one, which refers back to an earlier example. I think it was at the end of section 11. It was an example that I did to illustrate the ideal gas law, PV equals nRT. You had a diesel engine with a 20-to-1 compression ratio. And in the earlier example, you were supposed to calculate the final temperature. And it was just sort of given to you that the final pressure was 66 atmospheres. Well, this example is to see where that 66 atmospheres comes from. It wasn't just a number that I made up. That's what you would have if the gas was compressed adiabatically, which is, I mean, in a real engine, the cylinders are not wrapped in 3 feet of fiberglass. So it's not exactly an adiabatic process, but if you're only worried about the level of accuracy that we have for everything else in this course with all the frictionless surfaces we talk about and things like that, yeah, over the long haul, a lot of heat escapes from the cylinders, and that's why you have to have a cooling system with the radiator and all of that. But each individual stroke of the piston only lasts a fraction of a second. You know, if you're driving down the road and your engine is spinning at 2,000 revolutions per minute, and for the piston to go from the bottom to the top of the cylinder only takes half a revolution worth of time, not much heat can flow in such a short amount of time. So the amount of heat that escapes on each stroke of the piston is actually fairly small. It's just that as you drive the thing, it accumulates, you know? I mean, you're driving along going somewhere, it takes you half an hour. That's a lot of strokes of the piston and it adds up, and that's why you need a radiator. But you can drive a car for a few moments with the cooling system empty and get away with it. I wouldn't do it for very long unless you like buying new engines, but 10, 15 seconds, you don't need a radiator. You won't really hurt it. Wouldn't go any longer than that. Maybe 20 seconds. Anyhow, 13A. So anyhow, the point of that was just to say that because it happens quickly, this is approximately an adiabatic process. So we'll get at least a rough idea of the final pressure if we assume that it's adiabatic. If it's adiabatic, P1 times V1 to the gamma power is equal to P2 times V2 to the gamma power. P times V is a constant, like it says among other places on your formula sheet. Originally, the gas is at a pressure of 1 atmosphere. You first look at it just as the intake valve closes. So this air-fuel mixture has just arrived from the outside world, and the piston hasn't really moved much yet, and so atmospheric pressure is what you begin with. As with, this came up in that example at the end of section 11 also. The question didn't tell you V1 or V2, but all you need actually is their ratio, so that's okay. So we'll just keep calling it V1 because I don't have a number to fill in for it. And, it'll all come out all right in the end. The final pressure, P2, that's the thing I'm trying to determine. And the final volume equals the initial volume divided by 20. V2 equals V1 over 20. Question tells us that, tells us that. Okay. 1 times this is just V1 to the gamma. Over here, well, I should probably write it this way. If you have A over B to the n power, that equals A to the n over B to the n. And well, before I cancel things out, maybe it looks better if I do this. Multiply both sides by 20 to the gamma power. And then if you divide through by gone. So the actual volume doesn't matter. It's just the ratio is all that it depends on. Now we need a number to fill in for gamma. Once I know that, I'll have my answer. The final pressure is 20 to the gamma power. Well, the question says that you've got yeah, okay, there it is, air. Now you go to this table in the formula sheet here, and you start looking around and you start to panic because it doesn't say air anywhere. There's like 12 different gases listed there. None of them say air, but hopefully you are aware that air is basically a mixture of oxygen and nitrogen. There is a little bit of some other stuff, but 99% of the stuff in my lungs right now is either oxygen or nitrogen. So if you look on here, for oxygen, gamma equals 1.40. And for nitrogen, gamma equals 1.40. So if you have a mixture of 1.40 and 1.40, sure seems like that ought to average out to 1.40. And so you get your calculator and you raise 20 to the 1.4 power. If anybody's interested in ancient history, I could tell you how we did that back in the days before you had electronic calculators available. But yeah, you probably don't care about that. Actually, that's not completely obsolete information because the person who programs your calculator has to know how we used to do it by hand back in the days before there were calculators. Well, then there's a little paragraph down here at the bottom about how heat pumps work. So you compress the gas and it raises up the pressure, and this corresponds to a higher temperature, as we saw in that example at the end of section 11, okay? PV equals nRT, you put that higher pressure in there, and you solve for the final temperature, and it's red hot. And I said something back then about how that's why diesel engines don't need spark plugs. And that's one application of some of this stuff. Well, here's another one. You compress the gas like this, and it raises the temperature. Well, what if you then circulated the gas around through some coils of tubing? Heat would flow out through the metal walls of the tubing into the surrounding room. And if the tubing is long enough that it reaches room temperature at the other end of the tube, then what would happen if you kind of reverse the process? Okay, it's come back down to room temperature, but it's still at an elevated pressure. And then what happens if you let it expand? Well, if compressing it drove the temperature up, expanding it would let the temperature back down again. If it started at room temperature, then that would take you down somewhere below room temperature. And then what if you circulated that through the inside of some sort of a box, like the refrigerator in your kitchen? It could absorb heat from the stuff that's in there and then return to the compressor, and then the cycle repeats. And in this way, you could pump heat from the inside of the refrigerator to the outside of the refrigerator. Now, using air as the refrigerant, if you were really determined, you could get that to work, but it would be a horribly inefficient refrigerator. What works much better is something with a boiling point fairly close to room temperature, such as a member of the Freon family. I think they're just in the process of banning another one of these now. They got rid of one class of refrigerants back in the 1990s because it was destroying the ozone layer. And I think they're trying to get rid of the ones they've been using since then because it turns out to be an extremely potent greenhouse gas. But, well, that's not our issue right now, today, in this room here. The issue is just simply how does the thing make it cold inside your refrigerator? So, Freon has a boiling point. At atmospheric pressure, Freon is a gas at room temperature, but its boiling point is not that far below room temperature. If you apply some pressure, it'll liquefy. Boiling points are a function of pressure. I mean, you can make water boil at room temperature. You just get a jar of water, you put it inside a bell jar, hook it up to a vacuum pump, start sucking the air out, and the water will start boiling at 70 degrees Fahrenheit once the pressure gets low enough. So when you compress the Freon, it becomes a liquid because of the higher pressure. So as it flows through those coils of tubing on the outside of the refrigerator, it's a hot liquid in there, okay? And it gets to the end of that part of the system, and it's, well, as I said, it's radiated all its heat into the surrounding room to the point where it's come down to room temperature, but it's still at an elevated pressure. Well, what happens next is it passes through a really narrow little passageway, a little capillary tube, and that's what separates the high pressure part of the system from the low pressure part of the system. As soon as it gets into the low pressure part of the system, the Freon evaporates because under such low pressure, it would normally be a gas. So it boils basically. Evaporation is a cooling process. That's why you're so fond of sweating on hot days. As the water evaporates off of your skin, there's all that latent heat, the heat of vaporization, that when you make a liquid into a gas, it takes a lot of energy to make it change state. And so that thermal energy gets removed from your body, and that's why you sweat. And in a somewhat analogous process, the evaporation of the freon inside the tubing on the inside of the refrigerator is a cooling process. So it's not just the change in pressure that makes it get cold in there. Actually, the more significant effect is the change in state. But, you know, all of this stuff is involved also. It's part of the story. So anyhow, in that way, heat is pumped from the inside of the refrigerator to the outside of the refrigerator. And I think there's a question in the homework. If this one isn't in there, it probably ought to be, because it's one of those classic questions. Can you cool off your kitchen by leaving the refrigerator doors open on a hot day? And the answer is no. The refrigerator is a heat pump. You're just pumping heat out of the refrigerator into, I mean, yeah, you've got cold air coming out of the open refrigerator door, but you've got heat coming off the back of the refrigerator. All you're doing is pumping heat from the kitchen into the kitchen. The heat just goes around in a circle, and that's not going to work. If you cut a refrigerator-sized hole in the wall and park the refrigerator there so that the heat was given off to the exterior of the house, then you could cool off your kitchen that way. That's all an air conditioner is. You put the air conditioner in the window and it pumps heat from your living room to the outside. But if you just sit an air conditioner on a coffee table, it's not going to cool off your living room. And if you just open up the doors on a refrigerator that's sitting in the middle of your kitchen, it's not going to cool off the kitchen. So that's what all of this basically says. Again, with somewhat more concise phrasing than I just did standing here telling you about it. So all that's left for this first half of section 13 is I want you to work on example number 4, which will be on the screen very, very soon. And I'll go over it. And that's where we'll put the splice between the two halves of section 13. So it's pretty similar to the one that I just wrote out for you, except this time the gas involved is helium, not air. Nobody would ever have helium in a diesel engine. I mean, the fuel wouldn't burn. But you don't want to have all your examples be the same kind of gas, so I made it helium this time. And just to give it a slightly different twist, instead of being the one I did for you earlier, the gas was being compressed. Here it expands. It starts out at a high pressure and it expands to 18 times its original volume, and you're supposed to find the final pressure. And it's not really too terribly different than the one that I just did. So you pause it while I'm erasing the part of the blackboard here and work on it. And it would be better if I so same idea as before. P1 V1 to the gamma equals P2 V2 to the gamma. Gamma was 1.4 for air. You go into the table there and look it up. Gamma is 1.67 for helium. So fill in what the question tells us. P1, the original pressure is 1,000 kilopascals. I don't need to convert into pascals as long as, if you're not going to convert to standard units, you should keep an eye on the units and make sure bad things aren't happening. But if you keep an eye on the units here, what it turns out happens is just whatever unit you have on P1, that's the unit that'll be on P2 when you solve for it. V1 to the gamma power equals P2 times 18 V1 to the gamma power. And similar to, well, maybe I should write it out. A times b to the n power is equal to a to the n times b to the n. So v to the gamma cancels v to the gamma, just like before. You divide both sides by v to the gamma and it's gone. So you've got 1,000 equals P2 times 18 to the 1.67 power. That comes out 124.8. Divide both sides by that and you get your answer. A lot less pressure than what you started out with. Okay. Leave it here and I'll finish off probably tomorrow morning. I'll be able to record the rest of section 13.